It's my great pleasure to introduce my good friend and colleague, Dr. Thomas Eversberg, who is from Germany. I met him when he was working on his PhD thesis at the University of Montreal, where he worked on Wolf-Rayet stars with Tony Moffat. And Thomas has an interesting career because he finished his PhD, so he's a professional astronomer, but then left astronomy and now works for the German Space Agency. So he does project management and technology, space related. But he's still an astronomer, but he's an amateur astronomer. And if you look at his affiliation there, the stsci.de, that's a private observatory and it's his own. And he has an 80 centimeter telescope in his back garden. His interest really is spectroscopy, not imaging, it's spectroscopy. And he does a lot of work with other amateurs from Germany, from France, from other places, trying to get these people to do spectroscopy and then also helping out the professionals. So today he's going to talk about one of these ProAm campaigns, the professional amateur campaigns, which we did here using the Mons back in 2009-10 on a Wolf-Rayet star WR+140. So please, Thomas.
So I switch on my microphone. Everybody can hear me, I guess. Thanks for being here. This is really fun. And you see already amateur work reaches obviously the professional domain. You would expect, well, we go for this, but unfortunately we don't get such observing time. We are more or less this part. And you might ask, how can you do science with such a small backyard telescope that's ridiculously small? But we did. So first, I will introduce the amateur spectroscopic research work all over the world, and then I show you the data we obtained, the results we obtained from 2008-9 campaign. I know that most of you are aware of the situation here on Teide or La Palma. The site is excellent to do research, not in Germany, for instance. And the amateurs, they established groups, meanwhile, to perform observations on the continent, all over the world, and at professional sites, if possible. But you have to apply for time, for instance, of course. So, unfortunately, I don't want to exaggerate. Johan said there are amateurs all over the world, they are doing science, but in fact, this is a tiny group. Actually, there are two tiny groups. The first one is in Germany. This is the Amateur Astronomy Association in Germany, and this association has subsections, and one of the subsections is spectroscopy. There are, meanwhile, 250 registered for discussion forum members. And you see, we have everything there. We have an annual conference, we have workshops, we have beginners courses to push amateur spectroscopy, give it a push so that we get more and more interested people. The second community is ARAS, the astronomical ring for access to spectroscopy in France. There's also a big group. You know this, Alex, the Sheljak people who built these off-the-shelf spectrographs are one of the main players here in this group. And this was it. There are barely 3 or 4 people I know in the US. There is one single amateur spectroscopist in the Southern Hemisphere sitting in Melbourne and delivering professional data. In the suburbs of Melbourne. You don't believe it, but I'll show you. So this is a basic situation, but when you go into this group, then you will find real experts. I said to Alex, you would be happy to have such instrumental designers in your institute. For instance, you find people who build their own instrumentation. Here's a standard spectrograph. Here as well, this is my own for my first telescope. I sold it already. Here's a standard spectrograph off the shelf. And here as well, from Germany, this spectrograph has been designed by people from ESO and Max Planck Institute in Munich. They know what they do. And what you see here, this is, now come on, I press a button and no error. What's going on here with the technique? Oops, going back. So, I should find, here it is. This is a funny device. It's out of wood. It's a shell spectrograph out of wood. The designer is actually a physician. He has a practice, and he has to go to his people. If you have stomach pain or so, then you ask him, and he has to get away from his spectroscopy, but he loves astronomy, astronomical spectroscopy, and he designed this spectrograph on the left side. It's a prototype out of wood, and it works. On the right side is almost the same instrument from the off-the-shelf, from Sheljak Instruments, and this is a shell spectrograph ready to go, and you already think about buying. This is a good idea to do so. So you see, there is something going on in the amateur domain with respect to instrumental design. Fine, they are wonderful designers, but what do they do with this instrumentation? I say, from my experience, there is monitoring, surveys, and long-term campaigns. You cannot compete with a 10-inch telescope with a VLT. It's impossible. You won't get time, and so you have to use your own telescope, and the only goal you can do is spectroscopy, because you have bright stars in the sky. Second magnitude is fantastic. We reach 8th magnitude with this instrumentation, but we are not able to do major deep sky spectroscopy, say, of a galaxy or so. This is not true. We can, with lower resolution. I have even seen an amateur spectroscopist who did spectroscopy of a quasar. Not too bad. So, and he measured redshift, of course. Okay. Oops, there's something wrong. So I start with monitoring. Here's an example. Garik, you said you have 10 years of Rigel. Here's 10 years of the BE star Delta Scorpii. A BE star is actually, oops, I'm back. It's actually a B-type star with a material disk above the equator. Above the equator is mainly hydrogen, of course, some iron. So you see emission lines because this disk creates recombination lines in H-alpha. And you can measure the strength, means the equivalent width of the H-alpha line here on the bottom, on the left side. And what you see here in the sketch, they measured over almost 10 years the equivalent width of this very line. And interestingly, here the blue stuff is Ritter Observatory in the US. Oh, fantastic. They found variability, and then they stopped. And then the amateurs took over, and suddenly an explosion in light coming towards you with variability never seen before. This pure amateur work. Unexpected results. And they can be used to understand the variability of this H-alpha line, the emission line coming from the equatorial disk. The disk has a size of about 20 stellar radii. It's quite huge. And the brightest BE star, for instance, Gamma Cas, the central star in Cassiopeia, second magnitude, easy to reach for an amateur astronomer. A professional can never do this. You know that. How do you get 10 years? You go for it for 10 years, but when do you publish your first paper? So, yeah, after 10 years and you're out, you can go home. Well, perfect work, but there were only one paper. I'm sorry, I don't do that. So, only possible with amateurs. Second possibility is surveys. You might remember the Hipparcos satellite. It was an astrometric satellite, and amateurs supported these satellite observations to calibrate their data. Today we have COROT. COROT is this astroseismology device. Okay, they are looking for planets, but I'm not interested in planets. I'm interested in this vibration of the star. And here as well, this is from the balcony. Christian Bouy in France used his balcony observatory also for a BE star, and you see he delivers spectra, one spectrum after the other for the whole survey. And what you see here is a photospheric absorption. Why is it so broad? Because the star rotates like crazy. It rotates within 1 day. And then you see an emission line, and this emission line is narrower because it comes from the Keplerian disk above the equator. Right? But in emission, because it's a recommendation line. So this data quality is standard. This is a 6 magnitude star. I would say if you want to have a signal to noise of about, say, 150 with a resolving power of 1 angstrom, then you can reach 8th magnitude for these small telescopes within half an hour or so. This is reasonable. You can do science with it. It's not a problem at all. Okay. The third and major field, or one of the major fields, are long-term campaigns. You might have realized this result here. This is Epsilon Aurigae. Epsilon Aurigae, it's an F supergiant, and every 27 years it's occulted by a very strange object. We knew that this is possibly a material disk from another star, a disk out of dust. And this has been the very first direct imaging of the occultation with such a disk. You can see it here. Here is in 2008 on the left side. There's nothing. And then in November 2009, suddenly something happens in front of the star. And then on the right side, you see it's moving towards. Wait a minute, my error is there. So it's moving in front of the star itself. Nature article, fantastic. Really first-class observations, interferometric observations. Really fantastic. And the result was, oops, no, it's gone. And the result is we see a disk out of dust in front of this F supergiant, and the star in the disk is possibly a B5 star, B5 star. And every 27 years. You want to wait for 27 years? I don't think so. This is really boring. But Kloppenborg et al. They did, and they showed, this is a disk. But, I mean, I speak about 3 observations over 1 year, okay? What do you want to find out? This imaging. You will not get any information about an internal structure of the disk itself. It's impossible. It's just imaging. You can't do this. And then the amateurs come. Here's a shell observation of Christian Bouy from his home balcony in Toulouse. And you see, it's 8 months observations in 2009 with a 3-day increment. I don't want to go into details here. Here's the H alpha line, and here's the red part of the spectrum. The spectrum itself is much wider. They cover the whole wavelength range, visible wavelength range. But I would say science is in there. You can do science with it. And I never have seen such data before. So he used the off-the-shelf standards, a shell spectrograph, plugged it into this funny small telescope here on his balcony. I mean, really unbelievable. And he delivers. And what is also very exciting, this is Robin Leadbeater. You already mentioned him. This is really a crazy guy. He's an engineer. He has no astronomical education, no physical education in physics. And he observed Epsilon Aurigae from his backyard here. And this is a real situation here. This picture from his backyard is a real situation because he observed the star through the trees of the neighbor. I asked him once, Robin, when will you cut down these bloody trees? Yeah, one of the next nights I cut it down and then I see the star better. So this is a real situation. And what you also see is he detected the potassium 77 line, 7700 line. And he plotted the excess absorption, not the real absorption, but the excess during occultation. And he found a very strange step-like behavior of the line strength, the excess line strength. So he suggests that it's the whole disk has a kind of structure. Okay, this is only a sketch like Saturn rings, but it may be much more complicated. Impossible to observe with an interferometric state-of-the-art instrument with worldwide observations from any astronomer, professional astronomer. It's impossible. So this guy from his backyard with his small pooper here, yeah, he delivers real stuff, and so it's there. You can take it and interpret it and do science. So Another long-term campaign took place last year. Many of you know this strange instrument. It's up here on the mountain. It's the IC80. We applied for it, and again, it is a BE star. The BE star Delta Scorpii. Delta Scorpii has also, it's a BE star, as I said. It has an equatorial disk. But it's very interesting. A companion, a B-type companion, crashes every 11 years into this disk. And this is very important. I mean, you have the star, there's actually a spot in your field of view, there's nothing, you have to interpret your spectroscopic data. You need a kind of test vehicle, your finger. What is it here? Yeah? And you're very lucky if you find such a finger, and here it is. It's a binary. It crashes into the object you want to investigate. Fantastic. It disturbs it. What happens there? What is the structure of the disk? And we have been there for a week together with a professional PI, Anatoly Miroshnichenko from Greensboro, USA, with a number of amateurs. So I wrote together with Anatoly the proposal, probing the flying saucer. I mean, first it looks like a flying saucer, and second you have to keep awake the time allocation committee. Hey, here's something very important. So if you apply for telescope time, make fun of it. They sleep. You're the hundredth application out of 1,000 or so. So make a funny title. So we did. And we observed the helium-2 line, 4686, and the H-alpha line from the disk. And what we see here in our spectra, I cannot present the results, they are still in progress. But what you see here, this is a simulation of Atsuo Okazaki from Japan. It's a hydrodynamical simulation. The companion comes to the disk itself during periastron passage, but the movie doesn't come. Here it is. Disturbs the disk, and what you expect is actually a disturbance in your H-alpha profile, in the strength of the H-alpha profile, and in the radial velocities. Of course, part of it comes towards you, another goes away. And indeed, we didn't see a standard Keplerian orbit in my radial velocity data, but a double dip. Because of the strange behavior of the disk, it is disturbed and clumping is introduced. You see here, there's a clump coming towards the observer, another, say, clump is going away, and you have a completely different view in radial velocities, so to say. Okay, that was the last year campaign up here, data on the way. So if I take a resume according to these campaigns, the work of amateurs, they are enthusiastic. I always say to students, don't dare, don't be afraid. If you're an idiot, if you cannot calculate, if you're bad in mathematics, yeah, that makes it harder. But if you're enthusiastic, you overtake them all. So be enthusiastic and go forward. Believe in your enthusiasm, that you like to work in astronomy, and they do. And they do what is required. Johan asked me maybe, or Alex, you asked me, I need data, Garrick. Rigel data, I need Rigel data. So make an announcement in the discussion forum and they jump on. From the backyard, okay? Second, they have high technical skills. You would be happy to have such guys here on board because they are able to design instrumentation. They learn, they permanently learn. There's a quick availability for observations. If you have, say, an outburst, sometimes we have outburst alerts or supernova alerts. Since 2011, the discovery of a supernova is only accepted if you deliver a spectrum. Very important for the average observer. But this is important to know. Physical knowledge is limited. So if you want to perform a professional ProAm campaign, you need to give input, professional input. They have no idea about excitation numbers. They don't know, atomic energies whatsoever. I don't know, or non-LTE calculations. Even I don't know this. But, so you need to give some kind of input. A collaboration helps a lot, especially if you're the owner of a wonderful observing site with 0.7 arc-seeing seconds. This is really a scandal. Anyway. Okay, but of course you're here because of our campaign, We prefer 2008 to 2009. So I give you 2 slides. I give you a smell what I'm speaking about. We are mainly working, or we did work here at the observatory on massive stars. Massive stars are actually takes the sun. You blow it up to 40, 30 to 40, or even 120 masses. It's so heavy. It's a big star. The diameter, the size, is maybe 10 to 50 times the sun. And the temperature is 60,000 Kelvin or so. And the luminosity is about 1 million times the sun. You will get a sunburn there. So it's real. These beasts can be found in the upper Hertzsprung-Russell diagram. It's the O stars. Really big stuff. And Wolf-Rayet stars are actually almost the same. They are just the outcoming beasts when the O star finishes its hydrogen burning. So hydrogen is gone, and then it starts burning in other species. And what makes it so important is the interstellar contribution of metals. Metallicity in the environment is high, and here's a prominent example. I guess you know this already, of course. This bubble here coming out of the galaxy NGC blah blah blah. This is not coming from a black hole. It would be a jet, but this is really the origin. It's a cluster, a big cluster of massive stars breaking through the disk, the material disk of the galaxy, and enriches, obviously, the interstellar environment with heavy metals, with metals in general. So the reason that we are here are not only supernovae, also massive stars, because they enrich, they fire carbon into their environment, and they, of course, explode as a supernova. And what a Wolf-Rayet star in detail, as I said, it's an O-star descendant. It burns in different species up the energy period, helium, carbon, nitrogen burning, and because of their very strong luminosity, they reach the Eddington limit, and the atmosphere becomes unstable. So, and this unstable atmosphere results in a wind, in a supersonic wind above supersonic speed in the interstellar medium of about the order of 2,000 kilometers per second, and they lose about 100,000 solar masses in 1 year. Can you imagine? It's no, that's wrong, completely wrong. Every 100,000 years, blah, blah, blah. Okay. Sometimes I like to talk nonsense, and when you are awake, the wind actually is optically thick, this HST image, and in fact, you cannot see the stellar surface itself. You only find in the spectra emission lines. You do not find photospheric absorption lines, and the surface is hidden. You cannot see it. So it means you cannot Hertzsprung-Russell classify it. It's simply invisible. There's a specific classification, but not due to Hertzsprung-Russell. And as I said, contribution of metals to the interstellar medium. That are Wolf-Rayet stars, very short, very briefly described. A very interesting target can be found in the Cygnus constellation. In fact, there is one bright Wolf-Rayet star in the whole sky. This is a southern object, second magnitude, Gamma Velorum. We cannot see it. The next group is between 7 and 8 magnitudes. They are right here, high above in the sky, Cygnus in summer. And this is one of the stars. It's a Wolf-Rayet +O binary. As I described, I want to investigate the details of the stellar wind, and I need a finger to test what's going on. And here my finger is an O star. Also, a bright star with strong wind disturbs the Wolf-Rayet wind and wraps around the Wolf-Rayet, the strong Wolf-Rayet wind with higher wind momentum, it's much stronger, wraps around the O star a shock cone of material. Shock because we are at supersonic speeds. The Wolf-Rayet wind has 2,000 kilometers per second. The O star wind 2,000. It's a shock. So it wraps around a shock cone. Here in the sketch, you can see it on the lower left. This is the orbital situation. The Wolf-Rayet star is on the large orbit. It has lower mass than the O star because it lost a lot of material meanwhile, and wraps around the O star a shock cone. This dashed line is a line of sight. And here are some parameters. The kinetic wind energy is about 10,000 solar luminosity. It's quite something. The cone luminosity alone is 3,000 solar luminosities. And the period is about 8 years. And the last periastron passage for us, it was important, was in January 2009. So we have been interested to cover this periastron passage as long as possible. And we applied at Mons. Mons is really, I'll tell you later, we got 3.5 months complete time coverage. So we did this. But before we could do that, we had to establish a worldwide campaign. I mean, it's boring just to stay on the carbon-3 line or H-alpha line. You need to go to different wavelengths. It's much more important. You want to go to X-ray. Here's the Rossi timing, X-ray timing explorer. Come on, the arrow takes time. Here's the X-ray telescope. Infrared, we observed Wolf-Rayet 140 with UCURT. And the rest is visible. Here's Robin Leadbeater again. This is Homiat Pooper. Berthold Stober, this is the wooden shell spectrograph position. And so we use this and Mons at Teide with 8 teams. It was really fun because I established a group of 16 observers for 8 weeks. 16 observers for 3.5 months. Every team 2 weeks, and they loved it for $700 only, including the flight, including accommodation, rental car. Well, the meal was excluded, but they did it. They loved it. So they jumped on. We established a campaign and said, "Okay, let's go." So we did. But before you do this, you have to prepare yourself. Of course, you cannot just go to Mons. Mons is really, This is the situation at Mons. I mean, in the user manual, you find the description, the instrument is an eyepiece. Okay, you do not want to work with an eyepiece, or you want to work with a spectrograph. So we used an off-the-shelf spectrograph, but this spectrograph is dedicated to Celestron C8 telescope or C11 with f210, Mons has f215. The whole telescope parameters haven't been adjusted to this. You can't do this. So you have to adjust the telescope, and this is possible, basically. So we did this. First, we designed or we implemented a finding field of view with a switch mirror. I mean, you're looking to the star, and you do not find it. You want to put it onto your slit jaws of your spectrograph. How do you want to find your bloody star? With your charts. This is really... So you have to implement the device just to find, is the star there? Okay, stop, here we are. This was the first work, the second work we had. The first is a Shapley lens, a focal reducer to adapt the focal length. You have to do this. The third, this was really funny, we all loved this. It's not a go-to telescope, this is old-fashioned. Today you go to a shop, you buy your C8 or C11 or so, and it is computerized, everything's fine, and you press a button, it's there. Unfortunately, you do not know what you have done. You press the button. What's up with celestial mechanics? What are the angles in it? What is the spherical geometry or so? No clue. You do not learn this at the university. You have to take care by yourself. So this was really old-fashioned, and we designed. Fortunately, we had an engineer, a software engineer, and she manipulated the computer so that we have been in the observatory. We had the finding charts, found the star itself, and then we adjusted the circles, and then we had 10 minutes time. It was generous for 10 minutes time. And we switched off the motor. And the computer itself, it calculated the time when we had to switch on. And that was 10 minutes by default. And then we ran down, one was up, one was down, watching the clock. Now, click, and it was in there. So it was funny semi-go-to, so I don't know, I have no expression for it. It was simply fun. And they really loved it. And you had to climb on the ladder, and I was oh gosh, this was something. To do that, you have to be prepared. This is impossible via email. You cannot do this via email. So we established 2 workshops in Germany, not with our Portuguese colleagues because it was too far away. But so we established 2 workshops and to design everything, to discuss it. And here in this picture, this is Ottmar Stahl. He's a professional from Landessternwarte in Heidelberg. He supported us. He was not the scientific PI. Scientific PI was in Canada. He was away. So we had a number of discussions, including optics, techniques. Here's a box on the right side. Here are some very strange optical devices. Anyway, here's a two. So we prepared a box and we shipped it. Johan was on the island, so we have been in permanent exchange with IAC. It was Johan. And I remember I called you up. Everything arrived? Yes, everything's fine. It was not fine because the USB transponder of our camera failed. So I guess it got a cosmic particle during the flight or whatsoever. So we have been in trouble later. But we designed everything. This is very important. You have to go, if you cannot adapt your instruments to the telescope, you have to go to the machine shop. You need somebody who helps you out at the letting machine. It's so. So we did. And then we had to run. And here's the team, part of the team. Here's the wooden Echelle guy, the physician. Lothar Schanne is chemist. Thomas Bergmann, he was schoolboy. He was 18 then. And Felipe Dias, he came from Lisbon. He's the software engineer. And here's another Portuguese group. They had made fun of it. Like here, you can see they all become Nobel laureates for the caps on it. This is ridiculous. I mean, how can you sit with such caps in the control room? I don't know this guy. He's a stranger. He just wants to visit us. John Morrison, the technician. I never met John Morrison. I don't know his face. I only know this picture from the back. Okay, so, and then you acquire your data. You have your data, and we had to deal with Tony Moffat. Okay, we give you all the data, and the PI will be your PhD student. It was Rémi Fayette. He's still working on his PhD. We gave all the data to him, reduction, but reduction is not everything. You have to discuss everything. And second, amateurs want to learn. So it was quite clear we do not leave this going. I mean, we want to learn something. And the biggest fun is if you learn together, and especially at a specific place, not in Germany. This is ugly weather. So we decided to go to Portugal, having a workshop there, sitting together at Convento da Arrábida. We established the so-called Convento group with wind at the Convento da Arrábida. It was really fun. And, oops, come on. So this was the situation. We have been together discussing everything. We had a number of presentations. I also gave a talk about amateur work, blah, blah, blah. And then we discussed the results. Plus, we established also a round table discussion on the left side about future projects. This was really fun. I mean, there was a swimming pool there. This is not too bad. So this is important. And now finally I show you what came out here. The first what we did is a so-called broadband analysis. You have to see it is a binary star. In the spectrum is a mix of an emission line Wolf-Rayet spectrum and an absorption line O-star spectrum. We also had Echelle data from Observatoire de Haute-Provence. So we could combine all these data, number of spectra, to perform an analysis of the orbital parameters. So we did, and here's the situation. We have O-star absorption lines, and we could measure the radial velocities. And here's the global result. Here are other periastron passages on the left side. Come on. Where's my arrow? On the left side, the first 1993, you can see data from other observations in 2001, and here's our observation. You see directly, oh, these guys have more data. You can confirm you can find the parameters much better than before. So we did. If I blow up this part, only our observation, and you find here our result. And we could improve the orbital parameters significantly. But what I want to show you is, Here are data. The crosses are OHP, OMM, professional, professionals. But Three Hills and Stober, amateur observers. They actually vanish in this number of data. So what I want to say, the data delivered by amateurs are reasonable, and they can be used. That are reliable radial velocity data. This is important to know because you find an amateur spectroscopist, he tells you, oh, I can deliver radial velocities. Of course you don't believe him. This guy, he has no clue about measuring accurately and blah, blah. But if you find such guys working in these communities, I would recommend first to trust it. To test it, of course, you should compare it, but in our comparison, there's no difference. Of course, we weighted the data. OHP is 2-meter telescope. The accuracy is better. So we gave it a weight of, I remember, 0.3. And the amateur data, 0.15 or so. So weighting is important, and then you can increase the accuracy of your whole measurement. You don't have to keep it in mind, but I just presented here some first data from the orbital analysis. You see, we improved all data available here from these measurements, even the period, eccentricities there. A signs as a projected ellipse. So the inclination comes later. I will show you. Okay, that was broadband analysis. But of course, we want to perform line profile analysis. You need a spectrograph of high resolution to perform line profile analysis. And here we have a specific situation. We have a carbon-3 line at 5696. The big one here, this is, oh, where's my arrow? The arrow doesn't come. Ah, there it is. This line is a shock cone line. This line delivers an excess as soon as a shock cone is present. I'll show you. Oops. Here it is. So we made a time analysis. We stacked all our observations up here, and then we did residuals. Residuals easily to produce. You take the average of all of them and subtract the average from each individual spectrum. So you only have the excess, the additional emission from an event which takes place only then. And this is shock cone. So what you see here on the right side is the shock cone excess emission. And you can analyze it. You can check out what's going on here. So we did. So first we knew this is our periastron passage, and we had a limited time period to observe. And this is here the red bracket. So here it's this situation, the material is coming towards you. Now it's almost perpendicular to the line of sight, and here it goes away, right? And this is exactly what we can see here on the left side, or in the residuals, if the error comes. So, come on. Well, I guess the batteries are lower, so. Okay, in the central stacking, the central picture shows the residuals here, and you see at the bottom part, there is slightly an excess in the blue side. Material is coming towards you. It is created, this is there, suddenly it's there, and then it moves towards the red, and then it goes away. There's nothing anymore. And this reflects exactly this situation. Here the material comes towards you, more or less, then it goes to the central line, and here it goes away. And then the material, the excess emission is gone because of the separation of the two stars, right? By the way, if I've forgotten, if you have questions, you can stop me, okay? With the microphone, we can discuss this later, of course. But if you feel obliged, okay, I need to ask a question, otherwise this guy never comes back again, then do it. Feel free to do it. Ooh. Energy saving, very well. Okay, this is the situation. And to analyze this excess emission, there's a famous model, the so-called Lewis model. Siegfried Lewis was a really interesting person. He developed during his PhD a model to investigate the excess emission of such winds. And the model consists of an O star and a Wolf-Rayet star and a cone, a simplified cone around the O star, with a stream velocity along the shock cone emission and certain angles. And the most funny thing, I would say, is Siegfried Lewis was an amateur. He did his PhD when he was 60, because he was teacher of mathematics and physics at a school in Germany. So even that is a very famous model. I don't know how many citations he got, maybe 200 or 300. He was an amateur. But this is so, I love it. Okay, and if you do this, and you use these three parameters in there, you can do a fit to your data, the radial velocity fit of this small, tiny excess emission here, and the full width half maximum of your excess emission. Of course, the error bars are big because the quality of your data with a 50 centimeter telescope is not very enthusiastic. But anyway, you can do that. We did. And the dashed line is a result from the last periastron passage in 2001. And the dotted line is simply using the Lewis model. But Lewis designed a model for circular orbits. This Wolf-Rayet+O binary, Wolf-Rayet 140, has a highly eccentric orbit. So we have to do something. Because this angle, delta phi, will change during periastron passage. So it's moving around, it's slightly tilted this way. Here's the star, the Wolf-Rayet star. I'm almost the O star. It runs towards. But if you reach periastron passage, you're not passing like this, but you become faster and faster, right? So the angle tilts. If you take this into account, you can calculate the stuff. And here you see that this angle delta phi at the bottom, it changes drastically from about 2 degrees to almost 25 degrees. So it's tilted. This is important to know to get all the other parameters. If you don't do this, you lose it. And here are the results. So with the inclination is established, significantly improved. The stream velocity along the shock cone is improved. And all these parameters, we estimated the major half-axis because of sin I, and the masses of 2 stars also clearly improved. And eta is the wind momentum ratio. That means that the O star wind has only 4% of the momentum of that of the Wolf-Rayet star. Wolf-Rayet star wind is really strong, and it wraps around the shock cone around the O star. These are the results. Okay. As I said, we had observations from space with X-ray. We performed this in combination to the professional amateur work to get information about the radiation processes. And this is very interesting. Here's on the upper right, you see the counts between 2 and 10 keV. That is about 20 to 50 million Kelvin or so, something like that. It's quite hot. So here's periastron, and here it's reflected as well, right? So the counts increase, periastron passage increases, and suddenly there's a dramatic drop, almost to 0. It's gone. X-ray is gone. Now tell me what happens there. So it becomes hotter. These 2 stars are closer and closer together, and you would expect X-ray radiation increase like crazy. In fact, you expect an adiabatic behavior, which is here the dotted line in the lower diagram. If I get the arrow again. Oh, come on, there it is. This is the behavior for an adiabatic process. This is what you expect. No exchange with the environment. The whole energy goes into this X-ray radiation, but it doesn't. It doesn't work. Not at all. It vanishes. It's gone. Where is this energy gone? Well, if you check this out, we have the same process in a periastron passage on the left side, and what we covered is exactly this time period. So the dramatic drop in X-ray radiation starts when we find excess emission in the shock cone. There's a clear hint that we see a cooling effect. Radiation, X-ray radiation. The X-ray radiation field is cooled by the carbon-3 emission which suddenly occurs. And we also know from our observation, from our measurements, that this process is not adiabatic but isothermal. So the whole energy goes into the shock cone and blows it up. It's as closer to the star it comes, the bigger becomes the shock cone. It's isothermal due to our measurements here. That's very interesting. So you see this hot material, it cools down, and then we observed also, we got some photometric data. Here you can see how important photometry is. The old-fashioned photometry, so boring. What do you see? You see a lot. Here you see again the X-ray curve in red. And right after periastron passage, when this material is gone, then suddenly the broadband visibility drops by a certain amount of magnitudes. The star dims down, and this is dust, production of dust. So the material, the X-ray emission, the star is radiating like crazy, very hot temperatures, 50 million degrees, woo, woo, woo. Then comes periastron passage and the X-ray photons. Oh, shocking. I have to cool down because of carbon-3. Oh, okay, I go to carbon-3. Excess emission, great, power. And suddenly it goes and cools down to dust and floats along the shock cone and cools down. There are very famous observations of dust in the infrared, where you find the whole spiral around the system. We know this already. So we see a complete radiation process. And now you have the dust, and you go to this with infrared observations. Here are some UCURT observations. And after, right at periastron passage, you suddenly increase your excess absorption in infrared wavelengths. And this reflects the situation here at the star. You have two different environments. Here's a dense helium-rich Wolf-Rayet star wind, and here's O-star wind, low opacity. Here's optically thin, and there's optically thick. And suddenly, the trailing edge comes into the line of sight, bloop, excess absorption, additional absorption. So we confirmed the global opening angle of the whole system with UCURT data. Okay, basically that was it. But of course, I give you a resume. First, we improved the orbital parameters by a cross-correlation of all the absorption lines in all our data, standard and the shell spectroscopy. The second result is we improved the accuracy of the shock cone parameters via this amateur Lewis model. I really want to highlight this guy. He's meanwhile 80. I mean, the unbelievable guy. You find it sometimes on professional conferences and running around with his wife. Oh, it's fun. Third, we find adiabatic and isothermal processes in the wind from X-ray to infrared. That makes the multi-wavelengths campaign so important, so that we understand what's actually going on in the whole system. Otherwise, you know just part of it. And fourth, the global cone opening angle is confirmed. So that is what came out of our 50-centimeter rusty, bloody stuff telescope campaign here at Teide. But the key to success, as I said, data coverage over long time scales in multi-wavelengths. We fired onto this target for 3.5 months, actually even more with data from Canada and US. So this is very important. If you want to perform such a campaign, you have to know what you're doing here, and you have to bring together people. An amateur will never ever get any time at UCURT. It's impossible. So we invited Perry Williams from Edinburgh. Could you join us? Oh yeah, it's fun. Okay, he has been on our meeting. It was a very highlight there. Okay. Of course, we published. This is the present situation of our publications. The lower one, this is Sky and Telescope. This is the equivalent in Germany, Stellar Wind Tango on Tenerife. Here is our proceedings paper. Of course, if you do a workshop, you need to write proceedings papers. I have a hard time to convince the amateurs. Oh, no, I'm busy. I want to do it. No, you have to publish. Go. So Johan and me, we have been the editor, pushed them. It was an 80-page paper, yeah, of old talks. These three papers, this one, that one, and here, Liège, the Liège proceedings, we met there and described what was going on. And here's the core paper in monthly notices by Wolf-Rayet et al. And et al. Is a number of private addresses with such amounts. Oh, great. That's great. It's fun. So this is a really fun result here we published. This is not the end yet. Wolf-Rayet 140 has been at the horizon during our observations. As I said, it's a Cygnus object. But periastron passage took place in January, so it was there. Once I had to call my partner, hey, Noah, come up, look at this. And the telescope was right horizontal. We obtained spectra with 6 degrees, or 5 degrees with R mass 6 or so. It still worked. For an amateur, it's crazy, watching to the horizon. And it worked. It was so great. Okay, I realize that meanwhile, professionals, I have still something to tell you. Of course, we continue with our work. Oh, I'm already over my time. The next campaign we plan is in 2013, co-rotating interaction regions in Wolf-Rayet stars. This is not a Wolf-Rayet star here because you can see the surface. But you can see such structures around O stars. But we also find such structures at Wolf-Rayet stars. But you cannot see the surface. These structures are a direct link to the hidden surface. So we can obtain, hopefully, information about the rotational velocity. But the problem is these structures come and go. And we still do not know, do they come and go periodically or stochastically? We have to find out what's going on there. This is our next idea. 4 months. If you give me 4 months at IC80, give me VLT, it would be even better. So, okay. And this is already on the way. We possibly get time at Stella and OHP in France. We'll see what's coming out. And as I said, the professionals meanwhile realize what we can do. This is a statement of Doug Guys in Liège, you remember. Many of the special targets among the massive stars are relatively bright and can be observed even with small aperture telescopes with good instrumentation, as I said. Professional amateur collaborations hold great promise for extended observing campaigns on selected targets, such as the recent Convento Group collaboration on Wolf-Rayet 140. And Christophe Martayan said, what happens if Eta Carinae explodes next year? During the next 1,000 years, we expect an explosion in Eta Carinae. Something like that, next 10,000 years, I don't mind. But what happens if it takes place next year? You can get rid of your big telescopes because it's so bright, it will burn your CCDs, right? There was a remark from a professional in the very last word from the ProAm Mons campaign, from the team. Thank you very much. It was a pleasure to get this time. We know how much it was. I mean, we got 4 months. Can you imagine 3.5 months to these amateur idiots? They believed in us. I don't know. I guess you lied a lot or so. I don't know. And thank you for your attention.
Okay, so we have time for the questions.
That was too good. That was brilliant. Yeah. The Nobel Prize laureate here.
Well, I have one. Are you aware of any other ProAm campaign or something like that?
Sorry?
Are you aware of any other people working on this type of ProAm campaigns? Or do you think you are
We have, yes, of course, we had some ProAm campaigns. For instance, as I said at the very beginning, the monitoring stuff takes place for a number of BE stars. We have permanently alerts on new supernovae. Well, mainly BE stars, because the amateur community was born with BE stars. Yeah, I mean, they're easy to observe. They are bright, starting at 2nd magnitude and up to 4th magnitude. You have 300 or 400 BE stars. They're everywhere. And they have these prominent H-alpha emission lines. It makes it easy to detect. And we get some kind of support from the professional side. Epsilon Aurigae was one non-BE campaign, so I would estimate roughly, I don't know, maybe there are permanently 5 or 6 campaigns ongoing. These long-term campaigns are a bit different. You need to this is not monitoring. Monitoring and an equivalent this is actually very, very simple. You have to see there is an observer, he has an own spectrograph for 10 years or for 5 years, and he knows exactly what the spectrograph does. This is important. What does it do when I screw this here, or if I touch that? So it makes the data much more reliable if you have such a permanent observers. Professionals often say, this is dumb work. Well, in fact, from the procedure, that is true, but it's necessary. It's real science. So we do in this context, we do a lot. And these campaigns is that what I introduce is the next campaign on 2 Wolf-Rayet, the circumstellar interacting regions. And presently, right now, we are firing on Zeta Puppis. Zeta Puppis is the brightest OF star. There's emission lines. I have been on this star in '95 with CFHT. And that was the first discovery of clumping in any O star. OF means emission helium lines, and then you can see this. And now we want to try again. Did anything happen with the central reversal in this helium line? It's a southern object. We can go here, and we have one single amateur astronomer. He's in the suburbs of Melbourne, and he delivers excellent data. It's unbelievable. We see everything, and I was jumping when I got the email. Whoa, what's that? So, but it's limited indeed. Yeah, we have to push this idea into the amateur community. I tell them what you're doing with your deep sky imaging is really fantastic. This is great stuff. I personally am not interested to make a picture of the Ring Nebula as the millionth time. I prefer to do stuff I see first. So maybe we can convince. But these 2 communities in Germany and France, they do a great job presently. We'll see what happens in the US with their big Dobsonians. Okay. Thanks a lot.